Hey, physics fam, let's look at number 5 from 7-2, which is the potential energy and kinetic energy worksheet. You've got a 500 kilogram pig. So right away, I've got a mass of 500 kilograms, might need that, standing on the top of a muddy hill on a rainy day. Okay, here's my little piggy. Perfect. Terrible pig. The hill is 100 meters long with a vertical drop of 30. Okay. So it has a vertical drop of 30. So to me, that tells me that the height that this pig would go down if it did would be 30 meters. I don't know if the 100 meters long is going to be important. I'm going to keep an eye on that. The pig slips and slides down the hill. What is the pig's speed at the bottom of the hill? Wow, okay. So I'm going to look for the pig's eventual velocity on this one. Wow, okay. So what can we do? The hint it says is the law of conservation of energy. All right, so the conservation of energy tells me that the starting kinetic and potential energy is going to be equal to the final potential energy and kinetic energy added together, right? So there's the F's for final, the I's for initial. Now, right off the bat, if that pig is at the top of the hill, not moving, there's no kinetic energy to start with. And as that pig goes to the bottom of the hill, it'll be on the ground, so there'll be no potential energy. So what does that mean? It means that the initial potential energy of the pig is now going to be equal to the final energy, kinetic energy. So, can we use that to help solve for it? Absolutely. We know that potential energy is mass times gravity times height, and we know that kinetic energy is 1/2 mass times velocity squared. So let's start plugging in for that to solve for that final velocity of that pig. I'm going to switch colors here, and let's get to it. The pig is 500 kilograms. Gravity, G, is 9.8, and the height is 30 meters off the ground. That tells me my potential energy. Now, for the kinetic energy side, 1/2 times mass times velocity squared. 1/2 times the mass is 500 times velocity squared. Now I think all I have to do is solve for this. So I'm going to do my 500 times 9.8 times 30, and that's going to give me about 147,000. Now on this side, 1/2 times 500, I know half of 500 is 250. That's going to be times velocity squared. I'm going to need to divide 250 over to both sides so that I can get velocity squared by itself. V squared will be there. And 147,000 divided by 250 ends up being about 588. Now my velocity isn't alone, it's squared. So I better square root that sucker. But what I end up with is velocity by itself, and I get about 24.25 meters per second. So if this pig slid down, and of course we're assuming there's no friction, it was super slippery, the pig's final velocity would be about 24.25 meters per second. But again, we could have not solved for this unless we looked at the conservation of energy and realized that there was no starting kinetic energy and no ending potential, so that we could set these two, the initial potential and final kinetic, equal to each other. Just keep that in mind. But there we go, that was number 5. Looking at number 6 here. While on the moon, the Apollo astronauts enjoyed the effects of gravity much smaller than on the Earth. That's true. The moon's gravity is much smaller. Neil Armstrong jumped up on the moon with an initial speed of 1.51 meters per second to a height of 0.7 meters. What amount of gravitational acceleration did he experience? So that question, looking for G. Normally we use 9.8 for G, but since we're on the moon, that's not what we're going to experience. All right, let's look, of course, at what we're given. First of all, we have no mass, do we? I started writing an M there, but it's M for meters. So let's take a look at that. M for meters is a height. So height lets me eventually figure out potential energy, so maybe that'll help. And we also know that it starts off with an upward initial velocity of 1.51 meters per second. All right, wow. We don't have a lot of information here, but let's see if we can figure this out. I have a feeling this is going to have to do with the conservation of energy. If you think about it, the starting potential energy and kinetic energy of an astronaut is going to be equal to its final potential and kinetic energy. So let's think about this rationally. If this guy jumps up from the ground, first of all, he's on the ground, so initially there is no potential energy. It's going to be all kinetic energy. Then when he's at the very height of his jump, he'll stop for a split second because he'll be at the highest point of his jump, which means there'll be no kinetic energy and there'll be all potential. So to me, it looks like the initial kinetic energy is going to be equal to the final potential, which means I can set these equations equal to each other. 1/2 mv squared equals mgh, because that's potential. Now take a look. Will this astronaut's mass change at all at any time? No, he's just jumping up and down, right? So if that's the case, then mass cancels out because on each side it's the same. So I don't even need them. They're going to be equal to each other. Awesome. That was a math hack. Now if I do 1/2 times the velocity, 1.51 squared, equals gravity's acceleration, which I don't know. I'm going to solve for that, times the height of the jump, which is 0.7 meters. All of a sudden, I can solve for g now. To do that, I'm going to do 1/2 times 1.51 squared. And when I do that, I end up getting about 1.14 equals g times 0.7. I'm going to divide both sides by 0.7. Let me show my math to cross out that 0.7. So g is going to be left alone, and it's going to be 1.14 divided by 0.7. When I put that in my calculator, 1.14 divided by 0.7, I end up getting about 1.63 for my answer. So the gravitational acceleration is 1.63 meters per second squared. That's the answer I ended up getting. Now, that was a tough one because we didn't know we were going to have no mass, but it ended up canceling out anyways. We had to look at the conservation of energy and realize that the kinetic energy at the bottom was going to be equal to the total potential at the top, so that we can even set these equations equal to each other. So understanding the conservation of energy is very valuable here. But there we go. We crushed that one, number 6 in the books. Number 7, it says a pile driver is a device used to drive stakes in the ground. Yeah, pile driver is like this big cylinder that's dropped onto something, and then it just, boom, pounds it into the ground. Pile driver. So they're building a fence. They drop a pile driver that has a mass of 3,000 kilograms. Wow, so that's something heavy. 3,000 kilograms. And it's from a height of 8 meters. Wow, so big mass, big height. This is going to have a lot of potential energy. Now the overall net force, whoa, forces in this problem, is 5 times 10 to the 6th newtons. That's a lot of force. How far is the stake driven into the ground? Wow, so how far is it driven into the ground is really asking me its distance. How far did it move? Wow, what a wide variety of information here. So let's think about this. I do have mass and height, so I can figure out potential energy. So somewhere in my brain, potential energy is here. And then I've got force and distance. I know that's the equation for work. So how can I justify this somehow to figure it out? But then I remember, the work energy theorem says that the work done on an object is equal to its change in energy, which in this case is its change in potential. So I can literally set my potential energy equal to my work equation, which is force times distance. So I can start plugging in for that. I know my mass, 3,000. I know gravity on planet Earth is 9.8. And I know that the height is 8 meters. And I know my force is 5 times 10 to the 6th, right? So I can solve for D, can't I? Absolutely. To do that, let me do 3,000 times 9.8 times 8 gives you 235,200 equal to 5 times 10 to the 6th is 1, 2, 3, 4, 5, 6, right? 5 with 6 zeros after it. I'm going to divide by that, 5 with 1, 2, 3, 4, 5, 6 zeros after it. And I'm going to end up getting D is equal to, oh, by the way, if you heard but you didn't see, I just divided both sides 2, 3, 4, 5, by 5 times 10 to the 6th. 1, 2, 3, 4, 5, 6. Okay, that's why D is left by itself. But D is equal to 0.047 meters, which if you look, 1, 2, that's about 4.7 centimeters. So when you drop this pile driver, the fence went down almost 5 centimeters. That seems realistic to me. So there we go. Solve for D, but I had to use the energy work theorem. Energy work theorem says the work done on an object is also equal to its change in energy, which is why we could use that. All right, that was another example. Great job, physics fam. Go ahead and check out the next video if you want to find out or get any help for 8, 9, or 10. Be well.